Okay, so we're going to take a look at another question from the topic of ordinary differential equations. So now we're going to take a look at another series solution differential equation. This time we're going to attempt the following question. So our direction is solve, and we are told the equation is x squared plus 1 times y double prime plus x times y prime minus y is equal to 0. And we are going to do this with the assumption that some solution y of x is equal to the series, and this series is going to go from n equals 0 to infinity a n x to the n. So first we'll take the two derivatives of this series. So y prime of x is going to be equal to the sum from n equals 1 to infinity of n times a n times x to the n minus 1. Second derivative, y double prime of x, is going to be equal to the sum from n equals 2 to infinity of n minus 1 times n times a n times x to the n minus 2. So we've got our assumptions, our assumption derivatives, and now we're going to plug these all in. So we get, this implies that x squared times y double prime plus y double prime plus x times y prime minus y equals 0 becomes 0 equals x squared times the y double prime we found down here. This is the sum from n equals 2 to infinity n minus 1 times n times a n times x to the n minus 2. This is plus this derivative, n equals 2 up to infinity n minus 1 times n times a n times x to the n minus 2 plus x times y prime, this derivative here, the sum from n equals 1 to infinity of n times a n times x to the n minus 1 minus y, which is the function, n equals 0 to infinity times a n times x to the n. So this whole thing is equal to 0. So now we need to try and make the x terms have the same power. So ideally we want all the x terms to have a power something like x to the n, and we want all the sums preferably to start from 0 if that's possible. So this top expression, this one is pretty easy. The x squared gets multiplied into the x minus 2, so we get plus 2 minus 2. So this top one becomes x to the n straight away. It also has an n term and an n minus 1 term. So if n is 0 or if n is 1, this whole thing goes to 0. So we can start this from 0 if we want. So this implies that 0 is equal to the first one becomes the sum from n is 0 to infinity of n minus 1 times n times a n times x to the n. The second one, this one here, this one's going to be our problem one. We will have to shift it. So, but these two down the bottom, these will not be a problem. So we'll do these first and then we'll shift this one. So we've got plus x times x to the n minus 1 is x to the n. And we can make this power 0 because there's an n multiple in there. So plus n equals 0 to infinity n times a n times x to the n. And then we have minus the sum from n equals 0 to infinity of a n times x to the n. Now we need to shift this term here. So in order to shift this term, I might actually do it on the other screen. I might do it over here so I can keep my equations relatively orderly. So we have to shift the sum from n equals 2 to infinity n minus 1 times n times a to the a subscript n times x to the n minus 2. So what we're going to do is we're going to let n equal k plus 2, because k plus 2 minus 2 will give us a power of k. So when we do this, we find this becomes the sum from k plus 2 equals 2, well that's k equals 0 up to infinity, of k plus 2 minus 1, that's k plus 1, times k plus 2 times a subscript k plus 2 times x to the k. And then our last step here, we're going to let k become n. I'm just going to call k n again. This is a weird process, the shifting, but it does work. So this will give us the sum from n equals 0 to infinity times n plus 1 times n plus 2 times a subscript n plus 2 times x to the n. And then we need to add this on over here. So this is plus the sum from n equals 0 to infinity n plus 1 times n plus 2 times a subscript n plus 2 times x to the n. So these all have x to the n's in them, and they all start from 0 now. So we can factor the x to the n out. This gives us 0 is equal to x to the n times the sum from n equals 0 to infinity times n minus 1 times n times an, plus the sum from n equals 0 to infinity of n times an, minus the sum from n equals 0 to infinity of an, plus the sum from n equals 0 to infinity n plus 1 times n plus 2 times a subscript n plus 2. And this is what we've got. Now, for this to be equal to 0, either x is 0 or this other expression is 0. So we are going to assume the bracketed expression is 0. So this implies that the sum from n is 0 to infinity. We could compress this all into one sum as well, so we will do this at this stage. From n equals 0 up to infinity of n minus 1 times n times an, plus n times an, minus an, plus n plus 1 times n plus 2 times a subscript n plus 2. This is all equal to 0. So now what we're going to do is we're going to start letting n be particular values, and this is going to give us particular expressions in an and an plus 2. So we are going to let n equal 0. So this will cancel the first term and the second term. It will leave us with minus a0 plus 1 times 2, which is 2a2, is equal to 0. So this will give us a2 as a function of a0 if we rearrange it, minus a0 from both sides, divide by 2. This gives us a2 is a0 divided by 2. So this was when we let n equal 0. Now we might choose to let n equal 1. Just doing this sequentially. So we get this term cancels, and now we've got 1 times a1, that's a1, minus a1, and then we have 2 times 3, that's 6, 6 times a3, so we have plus 6a3 is equal to 0. Now the a1's cancel here, so this implies that a3 is equal to 0. Now if we're going to do quite a few of these, if we find that all of the even subscript terms are, if all the odd subscript terms are 0, this is potentially going to tell us that we have a specific solution. Then we'll be able to compare our solution to a list of known Taylor or Maclaurin expansions, and we may be able to identify a particular solution. It's fairly common for sines and cosines to only have, say for example, even terms or only have odd terms. It may not be the case that all of the odds are 0 here, but that is a telltale sign that you're after a specific solution. We also should say that we let a0 be a0, and we let A1 be A1. So these were definitions we started with. Then we've got A2 in terms of A0, we've got A3 in terms of A1, it's 0 in fact. Now we're going to let n equal 2. So we're going to let n equal 2. This gives us 2 minus 1, which is 1 times 2 times A2. So this will be 2A2 plus 2A2 minus A2. And then we have 3 times 4, that's 12 times A4 plus 12A4. This is all equal to 0. So this gives us 2 plus 2 is 4, minus 1 is 3. This is 3A2 plus 12A4. Now what we want to do here is we want to rearrange this so it's A4 as a function of A2. So this is 0. So this implies that 12A4 is equal to minus 3A2. Divide both sides by 12. And this gives us A4. 3 on 12 is 1/4. It's minus 1/4 A2. But we know that A2 is A0 on 2. So this is actually minus 1/4 times A0 on 2, which is minus A0 on 8. So we have 1/2 times A0, then we have minus 1/8 times A0. So we've done our two basic conditions here and here, then we've done n is 0, n is 1, n is 2. Let's do n is 3 and then see if we can identify if this is a known series. So we are going to let n equal 3. So if n is 3, we're going to get 3 minus 1 is 2. 2 times 3 is 6. 6A3. We have 6A3 plus 3A3 plus 3A3 minus A3 minus A3. And then our big expression, this one, becomes 4 times 5, that's 20, times A5. So this is plus 20 A5. This is all equal to 0. This implies 6 plus 3 is 9, minus 1 is 8. So we have 8A3 plus 20A5 is equal to 0. We can rewrite this as 20A5 is equal to minus 8A3. So this implies that A5 is minus 8A3 on 20. Now we have something dealing with A3 earlier. A3 is 0. So this is actually 0. So this tells us that A5 is 0. So we have an A1 term, which we have not yet defined. We have A3 is 0, A5 is 0, so likely all of the odd number terms are zeroed, but the even number terms aren't necessarily 0. So now we're going to write down what our solution form for this will look like. Now remember, the solution form is the sum from n is 0 to infinity a n x to the n. So therefore, our solution y of x should look something like a0 plus a1 times x plus a2 times x squared. Now a2 is a0 on 2. So this will be a0 on 2 times x squared plus a3 times x cubed. But a3 we found is 0. So this is 0 times x cubed. Plus we could have our fourth term. So our fifth term will be when n is 2. So here we found this will be a4 times x to the 4. Well, a4 we found was minus a0 on 8. So this is going to be minus a0 on 8 times x to the 4. And then we're going to have plus a5 times x to the 5, which is going to be 0x to the 5, and so on. So these terms cancel. And if we look at the terms that contain a0, they're all the even-powered terms. So if we choose to rewrite this, we could say y of x is actually equal to a1 times x, so some number times x, this is some solution, plus a0 times 1 plus 1/2 times x squared minus, we could have 1/8 x to the 4, and so on. So this is the form of the solution. Now this list of terms, we want to work out if we can identify what this is. So we need to look up our list of known Taylor expansions, and we just need to compare it to known Taylor expansions. So some of the known Taylor expansions include sine, cosine, e to the x, and so on. So if we have even powers, this could be cosine. So a cosine expansion, cosine of x, we know is 1 minus x squared on 2 factorial plus x to the 4 on 4 factorial minus x to the 6 on 6 factorial, and so on. This looks very similar to the expression that we have here. One problem is that the signs are wrong. So we would have to find a way to rearrange this in order to change the sign of the 1/2 and change the sign of the 1/8. Now this could also be an indicator that we have a mistake in our working. So we'll quickly come back up here and check our working. We said a0 was a0, a1 was a1. When we let n equal 0 from our expression, the first two cancelled, we got minus a0, and then we got 1 times 2, a2, so we got a2 minus a0 plus 2a2 is 0. This told us that a2 was a0 on 2. And then when we did n equals 2, we got 2 plus 2 minus 1. This 2 plus 2 minus 1 was 4, minus 1 is 3, and this became negative. So we had a4 was negative a2, and then a2 we knew was just a0 on 2. So there's nothing we can do to actually change the sign problem here, unless we also had a negative power in here. So we could have something like minus 1 to the n, a minus 1 to the n that's shifted. We could have something like a cosine x times minus 1 to the n minus 1, or something like this. So whatever the cosine terms are, then some of them shifted. But likely this is not actually going to be any known function, or if it is a known function, it's going to be a slightly more complicated variant of a function. And so this is the solution that we're after in its series form.